Welcome to this lecture of calculus. In this lecture, we shall learn about the indeterminate formula of limits. We already have the knowledge as how do we compute the limit of a function, and then we know how to evaluate the limit of the quotient of two functions. The general rule for evaluating the limit of quotient of two functions like f of x divided by g of x when x tends to a, this is usually given to be equal to f of a divided by g of a. But we will have noticed in many cases where this f of a divided by g of a becomes 0 by 0. In this case, we say the fraction f of x divided by g of x assumes the indeterminate form. So this is one of the indeterminate forms like 0 by 0. Similarly, we have some other indeterminate forms as well. Like we shall mention all of those indeterminate forms here and then discuss how to compute the limit in each case one by one. So first of all, we have 0 by 0, which is an indeterminate form. Then we may have the answer like infinity by infinity, which is also an indeterminate form. Similarly, we can have infinity minus infinity. We may have infinity power 0, or we may have 0 power 0, or we may have 1 power infinity. Now here we shall discuss a rule which helps us in evaluating the limit of the quotient of two functions when the substitution x equals a gives us one of these six forms. The rule for all of these forms is just one, which we call the L'Hopital's rule. We shall first define this rule for the indeterminate form 0 by 0. So let's take the form 0 by 0. Then in this case, the rule speaks like this: if f of x and g of x both vanish as x tends to a, then this limit x tends to a f of x divided by g of x, this is defined to be equal to limit x tends to a f dash of x divided by g dash of x. So the L'Hopital's rule tells us that if we have a 0 by 0 form, then we can evaluate this limit f of x divided by g of x by differentiating the numerator separately and differentiating the denominator separately. Then we will again put the value x equals a in the numerator and x equals a in the denominator. Now there is also a case that we may have f dash of a also equal to 0 and simultaneously g dash of a equal to 0. In that case, what we do, which I'll mention it here, but if f dash of a is equal to 0 and also g dash of a is also equal to 0, then we will further repeatedly apply the L'Hopital's rule. Then we will write limit x tends to a, this f dash of x divided by g dash of x. Now this will be equal to limit x tends to a. Now take the second derivative of f in the numerator and take the second derivative of g in the denominator. So this is a rule when the values f dash of a and g dash of a also become 0 when we put x equals a in this limit. So in that case, what we do, we will again differentiate the numerator separately and differentiate the denominator separately to get this double dash of a x divided by g double dash of x. Now when we substitute the value x equals a here and x equal to a in the denominator, if we get some appropriate value, we will call that is the limit of our function f of x divided by g of x. But if we again get f double dash of a equals 0 and g double dash of a equals 0, then we will again repeat the L'Hopital's rule and differentiate this f double dash of x again in the numerator and differentiate g double dash of x again in the denominator. So therefore, in general, what we learn by this rule, so thus we have to keep on repeatedly differentiating the numerator and the denominator until we get some appropriate function which is not in the indeterminate form. So therefore, limit x tends to a f of x divided by g of x. Now first of all, if we become a 0 by 0, we will write the limit as limit x tends to a f dash of x divided by g dash of x. Now when we differentiate, put the value of x equal to a in numerator as well as in the denominator. If we get some appropriate limit value, we will write that as our answer. But if we get f dash of a equal to 0 and g dash of a equal to 0, then we will put this limit again equal to limit x tends to a f double dash of x divided by g double dash of x. So again we will put x equal to a in the numerator and x equal to a in the denominator. If we got some appropriate limit, that will be the limit of the function. But if we got 0 by 0 again, we will again keep on differentiating it until we get a form which is not in the form 0 by 0. Now let's take one exercise to explain this rule more properly. Now let's take up the solution of these two one by one. The solution for the first one is, now here we have f of x, which is in the numerator is 1 minus cos x, and g of x is equal to 3x squared. Then obviously f of 0 is equal to 0 and g of 0 is equal to 0. Then f of 0 is equal to 1 minus cos 0, but we know that cos 0 is equal to 1, so it becomes 1 minus 1 equal to 0. And g of 0, which is obviously equal to 3 into 0 equal to 0. So therefore we have our limit in the form 0 to 0. So thus, using L'Hopital's rule, we have limit x tends to 0, 1 minus cos x divided by 3x square. Now as numerator become a 0 and denominator also become a 0 when we put x equals 0, so we will write this as limit x tends to 0. Now differentiate numerator with respect to x. The derivative of 1 is 0 minus the derivative of cos x is minus sin x, whole divided by, and the derivative of 3x square is 6x. So this becomes, this is equal to limit x tends to 0 sin x divided by 6. Now here in this function, we will again put x equal to 0. But when we put x equal to 0 in the numerator, we get sin 0, which is 0. And put x equal to 0 in the denominator, we again get 6 into 0, which is 0. So therefore, it's again in the form 0 by 0, which is again an indeterminate form. So therefore, we will again differentiate this function in the numerator as well as in the denominator. So therefore, again applying the L'Hopital's rule, so this becomes a limit x tends to 0. Now derivative of sin x is cos x in the numerator divided by derivative of 6x is 6 in the denominator. Now put x equal to 0 in numerator as well as in denominator. When we put x equal to 0 in numerator, we get cos 0, which is 1. So this is not the form 0 by 0. So therefore the answer is cos 0 divided by 6, which is equal to 1 divided by 6. Similarly, we can evaluate the second part, which is here, sin 2x divided by 3x. Now when we first of all put x equal to 0 in the numerator and denominator, we get 0 by 0 form. So then we have to differentiate this function using the L'Hopital's rule. So therefore, let's solve this second part quickly here. We have limit x tends to 0 sin 2x divided by 3x. This is equal to limit x tends to 0. Now derivative of sin 2x is 2 cos 2x divided by derivative of 3x is just equal to 3. Now when we put x equal to 0 in the numerator, we do not get 0, so therefore this is not in the indeterminate form. So therefore our answer is 2 cos 0 divided by 3, which is equal to 2 divided by 3. Now let's put some exercises here that you may practice yourself. So these are two exercises that you should try yourself. Now let's move forward and write out another indeterminate form, which is infinity by infinity. So therefore this is form 2. This is the form infinity by infinity. So again here using the L'Hopital's rule, we have again limit x tends to a f of x divided by g of x. Now this will again be equal to limit x tends to a f dash of x divided by g dash of x. So therefore there is no change in the rule for infinity by infinity, and the rule for 0 by 0 is exactly the same. Now as we did in the form 0 by 0, if we differentiate the numerator and denominator separately once, then when we put x equal to a here, so we get f dash a divided by g dash a. If this is again 0 by 0 form, then we can again differentiate it and get limit x tends to a f double dash of x divided by g double dash of x. And again we will substitute the value x equal to a in the second derivative in the numerator and denominator. If we again obtain an infinity by infinity, we will keep on differentiating the function until we do not get infinity by infinity, or the function does not get reduced to 0 by 0. So we have to keep on differentiating until the indeterminacy is removed. Now let's take up some exercises here as well. We shall here solve part number 2, and then part number 1 will be left as an exercise. So solution for the second part is, we have f of x, which is the numerator of this function, which is log x minus pi by 2, and g of x is equal to tan x. Then when we find f of pi by 2, we get log of pi by 2 minus pi by 2, which is equal to log 0, which is equal to minus infinity, because log 0 is infinity. Similarly, and when we evaluate g of pi by 2, we get tan pi by 2, and we also know that tan pi by 2 is equal to infinity. So we have the form infinity by infinity. And it doesn't matter whether we have negative infinity or positive infinity somewhere in the numerator or somewhere in the denominator. Whether it is plus or minus, it is just infinity. So therefore we have the case infinity by infinity. Hence, using the L'Hopital's rule, hence we use L'Hopital's rule. And the rule tells us that limit x tends to pi by 2 log of x minus pi by 2 whole divided by tan x. Now this is equal to limit x tends to pi by 2. Now differentiate numerator with respect to x. The derivative of log is equal to 1 divided by x, so it is 1 divided by x minus pi by 2. Then the derivative of x minus pi by 2 is 1. So now whole divided by the derivative of tan x is sec square x. So therefore we get this is equal to limit x tends to pi by 2. So we can write this as 1 divided by x minus pi by 2 into sec square x, which can easily be simplified into this form. This is limit x tends to pi by 2. Now 1 by sec square x, we know it is equal to cos square x, and in the denominator we have x minus pi by 2. Now when we look at this function, when we put x equal to pi by 2 now, we get cos square pi by 2 in the numerator and divided by pi by 2 minus pi by 2. And we know cos pi by 2 is equal to 0, so therefore we get 0 by 0, which is a 0 by 0 form. So thus when we were trying to remove the indeterminacy infinity by infinity, we call the indeterminacy 0 by 0. And again we will apply the L'Hopital's rule. So again apply L'Hopital's rule. We obtain limit x tends to pi by 2. The given function is log x minus pi by 2 whole divided by tan x. Now this was infinity by infinity case, and we differentiated it using the L'Hopital's rule and obtained the form cos square x divided by x minus pi by 2, which is now 0 by 0 form. So therefore we can apply the L'Hopital's rule, and this becomes limit x tends to pi by 2. Now derivative of cos square x, that is equal to twice cos x into derivative of cos x, that is equal to minus sin x whole divided by, now derivative of x is equal to 1 and derivative of pi by 2 is equal to 0. First simplify it like this, limit x tends to pi by 2. Now we know this is equal to minus 2 cos x into sin x divided by 1. Now put x equal to pi by 2, since cos pi by 2 is equal to 0 and sin pi by 2 is equal to 1, so therefore the answer is 0. Similarly, the first part log x divided by x can be solved by differentiating numerator and denominator separately using the L'Hopital's rule. Now let's come to define the form third, which is infinity minus infinity. If f of x and g of x become infinite, and x tends to a, then this f of x minus g of x assume the form assumes the form infinity minus infinity. Then we can simplify this case in this way: f of x minus g of x. Since this is an indeterminate form infinity minus infinity, we can convert it into the indeterminate form 0 by 0 in this way. We can write down this as 1 divided by g of x minus 1 divided by f of x whole divided by 1 divided by g of x into f of x. Now if we look at this expression on the right hand side, we will cross multiply this like this: f of x into 1, which becomes f of x, minus g of x into 1, and so it becomes g of x, the denominator f of x into g of x. So this is the numerator whole divided by 1 divided by g of x into f of x. So therefore we can clearly see the left hand side and right hand side are equal, because the g of x into f of x just cancel with this g of x into f of x. So this is the way how we can convert our infinity minus infinity form into 0 by 0 form, and then we can apply the L'Hopital's rule. Now let's take up an example here to explain this more properly. Now first of all, when we look at this limit, sec x is equal to infinity at pi by 2, and tan x is also equal to infinity at pi by 2. So therefore this is infinity minus infinity form. So therefore the solution here, f of x has been taken as sec x, and g of x is equal to tan x. Then f of pi by 2 is equal to infinity, is equal to infinite, and g of pi by 2, this is also infinite. Therefore we have infinity minus infinity form. So therefore, thus this limit x tends to pi by 2 sec x minus tan x, this is equal to infinity minus infinity, which is an indeterminate form. So what we in this case, so what we do in this case, so therefore we write this limit x tends to pi by 2 sec x minus tan x, this is equal to limit x tends to pi by 2. Now as we have explained above, we can write down this fx minus gx as 1 by gx minus 1 by fx divided by 1 divided by g of x into f of x. So therefore this is equal to 1 by gx. 1 by gx is 1 by tan x minus 1 divided by sec x whole divided by 1 divided by tan of x into sec x. This is the way how we convert our given indeterminate form infinity minus infinity into 0 by 0 form. Now we can write this as, this is equal to limit x tends to pi by 2. Now 1 by tan x can be written as cos x minus 1 by sec x can be written as cos x whole divided by, this is 1 by tan x which can be written as cos x into cos x. Now let's simplify this further. This is equal to limit x tends to pi by 2. Now cot x can be written as cos x divided by sin x, then minus cos x, similarly whole divided by cot x can be written as cos x divided by sin x into cos x. Now simplifying this further, this becomes limit x tends to pi by 2. Now we can take this cos x common from the numerator of the numerator. So this is cos x into 1 divided by sin x minus cos x whole divided by, we can write this as cos x into cos x into 1 divided by sin x, and this can be written as limit x tends to pi by 2. Now this is cos x in the numerator, this is cos x in the denominator, we can cancel it, and the remaining is that we are left with, unfortunately this is 1 here, so we are left with 1 minus sin x divided by sin x whole divided by cos x divided by sin x. Now in this expression, the sin x in the numerator, this sin x in the denominator becomes cancelled. So we are left with limit x tends to pi by 2 1 minus sin x divided by cos x. Now here when we put x equal to pi by 2, we get 1 minus 1 equal to 0. When we put x equal to pi by 2, we get cos pi by 2, that's again equal to 0. So we can apply the L'Hospital rule, which is equal to 0 by 0 for. So we apply the L'Hospital rule, so therefore this is equal to limit x tends to pi by 2. Now derivative of 1 is 0 minus derivative of sin x is cos x, 4 divided by the derivative of cos x is sin x. Therefore this becomes 1 minus cos pi by 2 whole divided by sin pi by 2. Now this is 1 minus cos pi by 2 is equal to 0, whole divided by sin pi by 2 is 1. So therefore this is equal to 1. Now we take the other indeterminate forms. We have a similar rule for all the remaining forms. So we have the forms like 0 by 0, infinity power 0, and 1 power infinity. For all of these, what we do, we use logarithms. We use the logarithmic function. And we shall explain all of these three indeterminate forms using examples only. Now in these expressions, if we obtain an indeterminate form of this, one of these 0 power 0, infinity power 0, 1 power infinity, then we will use logarithms. Let us solve the first part here. Solution. So in the first part, we have limit x tends to 0, 1 plus x power 1 divided by x. Now when we put x equal to 0 here, which is equal to 1 power infinity. So this is 1 power infinity form. So what we do, now let this u is equal to limit x tends to 0, 1 plus x power 1 divided by x. Suppose the limit is equal to u. Then we apply log on both sides. So apply log on both sides. We obtain, so we will get log u is equal to limit x tends to 0, log of 1 plus x power 1 divided by x. Now we shall evaluate this on the right hand side. This is equal to limit x tends to 0. Now we know log m power n is equal to m log n, so this becomes 1 divided by x log of 1 plus x. So the rule that we have used is log m power n is actually equal to n log m. Now we can write this expression as limit x tends to 0, log of 1 plus x whole divided by x. So we have obtained our limit in the form of a fraction function or a quotient function. When we put x equal to 0, we get log 1 divided by 0, but log 1 is also equal to 0, so we got 0 by 0 form. So which is equal to 0 by 0 form. And we know what we do in the 0 by 0 form, we use L'Hospital's rule. So therefore this is equal to limit x tends to 0. Now derivative of log of 1 plus x, that is 1 divided by 1 plus x, whole divided by derivative of x is equal to 1. So this becomes limit x tends to 0, 1 divided by 1 plus x. Now when we put x equal to 0, we get x equal to 1. So that's what we have obtained. Thus log u is equal to 1. So this implies u is equal to e power 1, or we can say this is equal to e. So therefore the limit of our given function is, therefore limit x tends to 0, 1 plus x power 1 by x, this is actually equal to e. Now similarly we can evaluate the remaining parts here. We will again write down the second limit as, when we put x equal to 0, we get this limit sin x by x, which we know as incident or limit, this is equal to 1. So therefore in this case we get 1 power 1 by 0, which is 1 power infinity. Then we will apply the log on both sides, and we can reduce this function into 0 by 0 or infinity by infinity, and then we can use the L'Hospital's rule. Similarly here in the third case, when we put x equal to 0, we get 0 power 0. Then applying the logarithm, we will get it converted into 0 divided by 0, which is the indeterminate form, and we can apply L'Hospital's rule similarly. So therefore in this way we can read the remaining parts and exercises, and this completes the indeterminate forms until this.